For Lesson 8, we're going to be looking at covalent compounds and molecular structures. So we will start by talking about valence electrons and identifying the number of valence electrons for a compound. Once we have that, we'll learn how to apply that to draw Lewis dot structures of molecules. Now, when we're drawing Lewis dot structures of molecules, we're going to need to be able to decipher between ionic and covalent bonding. So we're going to be bringing back those definitions and applying those as well. So there are going to be no equations in this lesson, as you can see, but a lot of new vocabulary terms that we're going to be discussing. Let's start by describing a chemical bond and talking about exactly what's happening on the atomic level. So with all chemical bonds, it's a form of attraction between any two atoms in a compound. Now, the important part of this attraction is that it must overcome the repulsion of the positively charged nuclei of the two atoms. Because when you bring two atoms close together, you're also bringing those two positively charged nuclei together as well. So there is some repulsion since positive charges are going to repel each other. So the attraction has to be stronger than the repulsion, is what we're saying there. There's also going to be an interaction between valence electrons. So if you remember from last chapter when we talked about valence electrons were the electrons in the outermost shell of the atom. Those are the electrons that have the highest energy because they were furthest away from the nucleus. And they're the easiest to pull off if we're trying to make an ion of some sort because they're not held as tightly. Quick review on the types of bonds that we have talked about so far. So ionic bonds. Ionic bonds we've discussed obviously are between ions. We usually see ionic bonds between a metal and a nonmetal, but remember we can also see them with two polyatomics together. And sometimes if we have two polyatomics together, it will consist of all nonmetals, but since the polyatomics themselves are charged, are ions, it's still an ionic bond. So what holds an ionic bond together? So what holds an ionic bond together is the electrostatic attractions between the ions. So we have a positively charged cation and a negatively charged anion. So due to these opposite charges, they're attracted to each other, and that's what holds it together. Now, ionic bonds are dependent upon the transfer of electrons because in order to get ions in the first place, you either need to gain electrons to become negatively charged or lose electrons to become positively charged. Now, covalent bonds, this is the one we're going to focus on most when we're drawing our Lewis structures. We will look at ionic bonds as well, but mostly covalent because the electrons are shared in covalent bonds. So we're not seeing any transfer of electrons. We're just seeing them share. And this is most frequently between nonmetals. You can see the examples below of water and ammonia. Now, a third type that I don't think we've discussed yet is metallic bonds. Just to know they exist is the main point here. So metallic bonds are between two metals, as you can guess, since they're metallic. And in metallic bonds, the electrons actually move freely through a medium. So all you need to know about metallic bonds really is that they exist and they're between two metals. We're not going to be discussing them much further. Now bonding, whether we're talking about ionic bonds or covalent bonds, are dependent upon the octet rule. So what is the octet rule? The octet rule is the tendency of main group atoms to obtain 8 valence electrons in their outer shell. Okay, now what does that mean? So first off, when we're talking about main group atoms, remember main group atoms are going to be the S block and the P block. So the ones highlighted in this red-orange color in this version of the periodic table here, those are the main group elements. So groups 1 through 8. So essentially what I'm saying is we're ignoring the transition metals, the transition elements in the middle. So all of the main group elements, their goal when they're happiest is when they have 8 electrons in their outermost shell, their valence electrons. Okay, why? Why is that when they're happiest? Well, let's look at this. So looking at the noble gases. So remember the noble gases are in group 8 here. The noble gases are very stable. That is a property that they have in common. They're very stable. Why are they stable? Because all of the noble gases have a full octet. They have 8 valence electrons in their outer shell, with the exception of helium. Because remember, helium is this first guy right here. Helium only has a s orbital, and remember, s orbitals can only hold a max of 2 electrons. So helium has 2 electrons in its valence shell, but all of the other noble gases have 8. So they're happy, they're stable. So since those noble gases are happy and stable, essentially the other main group elements want to be a noble gas. That's their goal. They want to get 8 valence electrons in their outer shells so that they can be just as stable as those noble gases. So in summary, for the octet rule, atoms will either gain, lose, or share electrons to achieve 8 valence electrons. Remember, there's always exceptions to every rule that we've learned in chemistry. So what are the exceptions for the octet rule? We'll look at them more closely later, but right now I want you to note 2, hydrogen and helium. So you saw helium on the previous slide, since that was one of the noble gases, but it doesn't have 8 valence, it only has 2. Hydrogen is going to be the same since it only has a 1s orbital. It's only going to have a max of 2 electrons. It's not going to be able to get up to 8, at least not in this course. Another important thing to note, which I didn't make clear on the last slide, was that the valence electrons for individual atoms is going to be equal to the group number. Now, this only applies to the main group metals. So what do I mean by that? Group 1, alkali metals, all of those will have 1 valence electron, including hydrogen. Hydrogen only has 1 valence electron as well. Group 2, the alkali earth metals, all of those are going to have 2 valence electrons. So on and so forth, all the way until you get down to the noble gases. So whatever group it's in for the main group metals, or excuse me, main group elements, not just the metals, that is how many valence electrons it will have. So the next question is, how do these main group elements reach an octet? How do they go about reaching an octet? So the metals, of course, are going to be a little bit different in reaching their octet than the non-metals. So we're going to look at an example of a metal and how it reaches its octet, and then we'll look at an example of a non-metal and how that reaches its octet. So what we're looking at first is an ionic bonding situation. So for sodium, since we're talking about metals, obviously, so for sodium, sodium has 11 electrons. How do I know that? Well, sodium is number 11 on the periodic table. Since it's number 11, that means it has 11 protons in its nucleus, as you can see from this depiction of the atom. So protons are positively charged. In order for the atom to be neutral, that means we have to have 11 electrons in order to cancel out that 11 positive charges. So now let's look at the shells around the nucleus. So sodium, you can see it's 11 electrons represented here with these black spheres with a negative sign in them. Now notice in its outermost shell, so in sodium's outermost shell that's highlighted in pink here, that is where the valence electrons are going to reside, because valence electrons only reside in the outermost shell. And you'll notice that sodium only has 1 valence electron in that outermost shell. So how does sodium go about reaching an octet? It has 2 choices. It's either going to lose that 1 electron, or it's going to have to gain 7 more to reach a full octet. Now, gaining 7 electrons, as we saw when we looked at ionization energy and electron affinity, is going to be extremely difficult. That's going to take a lot of energy to gain that many. However, it'd be much easier for that sodium atom to lose 1 electron. And that's what it does. And what happens when it loses that 1 electron? Well, then there's no more electrons in that original outer shell. Now it has a new outer shell. So looking at its new outer shell, highlighted in blue here, if you count the electrons on its new outer shell, it has 1, 2, 3, 4, 5, 6, 7, 8. So now it has a full octet, and it is happy. And you'll also notice that it is isoelectronic, or will have the same electron configuration now as the noble gas in the row above it, which is the neon atom. So what we see from this is metals tend to lose valence electrons to complete their full octet. Let's look now at a nonmetal. So in this example, we have chlorine as the nonmetal. So nonmetals we know like to gain electrons. So we can guess what's going to happen to the chlorine atom when it wants to get a full octet. So looking at its outer shell, chlorine having a total of 17 electrons. But how many of those electrons are valence? Well, if we look and count around that pink shell, it has 7 valence electrons currently when it's neutral. So what it's going to do is it's going to either lose all 7 of those or gain 1 to get a full octet. It's much easier to gain 1 than it is to lose 7, so it gains an electron. Now it has 8 electrons in its valence shell and a total of 18 total electrons. Since it gained an electron, it now has a negative charge, just like sodium has a positive charge when it loses an electron. And you can see that chlorine now, that it has 18 electrons, is isoelectronic with a noble gas in the same row, being argon. So since it's isoelectronic with argon, that's just showing it is now more stable. Oftentimes we want to represent atoms and their valence electrons, and we don't want to draw a depiction of the atom similar to one on the previous slide where we have to draw all of the rings, including everything. So instead what we do is we draw what we call a Lewis dot structure. And a Lewis dot structure shows the arrangement of the valence electrons along with the element symbol. So looking at a group here of elements on the periodic table. So we're going across the periodic table. Starting in group 1, going all the way to group 8, and showing how the Lewis dot structures are going to look for these. Now I want to point out that, for instance, like group 1 has 1 valence electron, as you can see from the depiction of lithium with 1 dot by it. All of the atoms in group 1 are also going to have 1 valence electron, so they're going to look just like this depiction with 1 dot by it. The only thing that will change will be the symbol itself. So for instance, if we're talking about sodium instead of lithium, it'll be Na with 1 dot by it. Now moving to group 2. Group 2 has 2 valence electrons, so what we do is we put 2 dots. Group 3, 3 valence electrons, so on and so forth. Now one thing I want to point out is the position of these dots are intentional. However, when I'm asking you to give me a Lewis dot structure, it does not matter to me where you put the dots, as long as you only have a max of 2 dots on each side. So looking at neon, for instance, neon having its full octet because it's a noble gas, you can see that it has 2 dots representing the electrons, the valence electrons to be more specific, on each of the 4 sides of that symbol. So why is it important to only have a max of 2 dots on each side? Well, because when we talked about electrons and how they fill orbitals, there's a max of 2 electrons in each orbital. So we don't want to put more than 2 electrons on each side because we're kind of representing the orbitals when we're doing these depictions. Now I also want to note that it is intentional for the other Lewis dot structures of where the dots are put. For instance, with boron, so looking at boron, they put 1 dot up here. Now, what if you put the dot on a different side? That's fine. It doesn't matter where it goes, as long as you have a total of 3 and no more than 2 dots on each side. Now let's look at ions and how we would draw Lewis dot structures for ions. So drawing Lewis dot structures for ions, you'll notice for the main group metals, not only do we have them in brackets with a charge on the outside of the brackets, but there are no dots around the metals. Why are there no dots around the metals? Well, because rubidium, for instance, is in group 1. So if it was neutral, so we have neutral rubidium, for instance, what would that Lewis dot structure look like? Rubidium's Lewis dot structure, if it was neutral, would have one dot, just like lithium did. Well, what happens when rubidium forms an ion? Well, since it's a metal, it's going to want to lose one valence electron to gain its full octet. When it loses that one valence electron, it gets a positive charge, but now that one dot is gone. That one valence electron is gone because it lost it. So that's why its depiction has no dots. And that's only for the metals where we're going to see no dots when they form their ions, no valence electrons when they form their ions. That does not mean they don't have a full octet. It just means the original shell with their valence electrons is no longer there, and those electrons are no longer there because it gave them away. Okay, now looking at the nonmetals. Now notice all of the nonmetals, ions, along with brackets and the charge on the outside of the bracket, they all have 8 dots around them. Why? Because they all have a full octet as well. But they gained electrons to get their full octet, so those 8 electrons are still represented around them. Also take of note, the 8 electrons they have a max of 2 electrons on each side. So important things to note with ions. First off, always have a brackets with the charge on the outside of the symbol to indicate that it is in fact an ion. Another important thing to note, metals, when they form ions for the main group metals, usually don't have any dots around them because they usually give all of those electrons away. The nonmetals usually have 8 electrons around them when they are ions because they gained electrons to get a full octet. So let's apply this to an actual compound. So we just looked at Lewis dot structures, and now let's look at Lewis structures for ionic compounds. So 2 examples that we have here are sodium fluoride and calcium sulfide. So how do we depict the Lewis structure for these? Well, we draw the ions of each in their brackets with their charges and what they look like. So for instance, sodium. Sodium has 1 valence electron when it's neutral, but when it forms an ion, it gives away that 1 valence electron, and in this case, it's actually giving that 1 valence electron to fluorine. That's why they're bonded. So it gives that 1 valence electron away, so we write it with Na, brackets around it, and a plus sign on the outside. Now for the fluorine. Fluorine has 7 valence electrons when it's neutral. All halogens will have 7 valence electrons when they're neutral. But since it gained an electron from that sodium, it's now going to have 8 valence electrons, so we depict that by putting 8 dots around the fluorine, putting the fluorine in brackets, and then the negative sign on the outside. Now let's look at calcium. So calcium is in group 2. It has 2 valence electrons, so it's going to lose those 2 valence electrons to become calcium 2+. So when we depict its Lewis structure, we put the calcium in brackets with a 2+ sign on the outside, indicating it no longer has those 2 valence electrons. It gives those 2 valence electrons then to sulfur. So sulfur, if you look on the periodic table, has 6 valence electrons, as all elements in group 6 will have. So since it has 6, it wants a full octet, so it takes those 2 that calcium gave away so that now it has 8. Once it has 8, since it added 2 negatively charged electrons to it, it's going to have a -2 charge, and we put it in brackets with the charge on the outside and the 8 valence electrons depicted around sulfur with dots. Now if you had to calculate the total valence electrons, in this case then, for these 2 examples, for the sodium fluoride, we have 1 sodium electron. We call it 0 valence electrons because it got rid of the 1 in its original electron shell. It still has a full octet, but it counts as 0 because the 1 from its original electron shell is no longer there. Then we have 1 fluorine that has 8 valence electrons. So the total is going to be 8 for this particular compound. Calcium sulfide, you'll notice in this case, is also going to have 8 for the same reasons. So let's go over some Lewis structure rules before we do more examples. So we saw a Lewis structure of an ionic compound on the previous slide. They get a little more complicated when we're doing covalent compounds. So we want to go over some steps or rules to help guide us. The first step is counting the total valence electrons. So how do you count the total valence electrons? You do that based off of the molecular formula given to you. You use that molecular formula given to you, and the elements in that molecular formula, you find how many valence electrons each of them can contribute based off of where they are on the periodic table. Important things to note: if it's an anion, for instance, meaning it has a negative charge by it, you need to add electrons to that total count. So if it's a -2, for instance, you'll add 2 electrons at the end for that charge that is present. If there are any cations, so if you're dealing with a cation, meaning a positive charge, you need to then subtract out that positive charge. So if you have a +3 charge on a compound, you need to subtract that from your total valence electron count, because that means we have 3 less electrons than we would think if it was neutral. Looking at step 2, next you need to arrange the atoms. So how do you arrange them? Well, you need to figure out which one is the central atom. Now, the central atom is almost always the first element present in the molecular formula. So that would be your central atom, and then all the other atoms are going to go around that central atom. Another way to figure it out is that it's the least electronegative element. So you can use your knowledge of the electronegativity trends to figure out which atom in that molecular formula is the least electronegative. I tend to just use the first atom present in the molecular formula because that's almost always the least electronegative element. The exception, of course, since there's always exceptions, is hydrogen. So if hydrogen is the first atom present in the molecular formula, don't put it as the central atom. We will not see hydrogen being the central atom in this course. Hydrogen will only be a terminal atom. Once you have the arrangement set up, so you know what the central atom is, and you have drawn or written all the symbols of the other atoms around that central atom, the next step is to connect all of those atoms with a single bond. How do we do that? We do that by drawing a line between them. So the line represents the bond. Now, we only do this step for covalent compounds, so we're not going to do it for ionic Lewis structures. So it's just for covalent Lewis structures, and that's mainly what we're focusing on when we draw these. So why do we draw a line? Because they're sharing electrons for covalent bonds. And that bond, that line, represents 2 electrons. Okay, so every line you see counts as 2 electrons. So if we do a double bond, for instance, it's going to count as 4 electrons because a double bond will have 2 lines. Once you're done with that step, next, we take any remaining electrons that we have from our original valence electron count, and we add those to the terminal atoms. And we do so in a way to satisfy the octet. So what I mean by that is we're going to be adding dots around the terminal atoms to make sure they have 8 electrons total, including the bond itself. The line that's attached to the central atom counts as some electrons as well. So once the terminal atoms are happy, once all the terminal atoms have their 8 electrons around them, if there are any leftover electrons, sometimes there are, sometimes there aren't, those leftover electrons are going to go on the central element. Next then is to determine if multiple bonds are necessary. If you are unsure what the central atom is, so for instance, if the first atom present, you're just like in the molecular formula and you think, I'm not sure if that's the central atom, feel free to use this electronegativity chart to figure out or confirm that the first atom present in the molecular formula is indeed the least electronegative. So you can see the electronegativity trend is increasing as we go from left to right across the periodic table, with the most electronegative atom being fluorine on the periodic table, and the least electronegative atom being cesium and francium in this bottom corner. So as we said earlier, covalent bonding is occurs and is formed by the sharing of electrons. So the attractive forces of the electrons to the nuclei are stronger than the electron-electron repulsion. So what I mean by that, if you bring two atoms close together, you're bringing their electron clouds together as well. So those electron clouds are going to be repelling each other. But the attractive forces need to outweigh the repulsive forces. Now, in covalent bonding, we're not just going to see single bonds. We are sometimes going to see double bonds or even triple bonds. In this course, we're not going to see any higher than triple. So single bonds. Single bonds are going to be longer and weaker than double and triple bonds. Triple bond is going to be the shortest and the strongest. Here is how we draw single, double, and triple bonds. So single bonds would be 1 dash, double bonds would be 2 dashes or 2 lines, and then a triple bond would be 3 dashes or 3 lines. So one way I like to remember whether the difference between single and triple bonds is I like to think of rubber bands around two balls. Okay, so the two balls representing atoms and the rubber bands representing the bonds. So if you put one rubber band around those two balls and you try to pull the balls apart with the rubber band on them, you will find that you'll actually be able to pull those balls pretty far apart. It's because that single bond can be long and weak. Now, if you add a second rubber band around those two balls and try to pull them apart, it's going to be a little bit harder, and you're not going to be able to pull them apart as far. So a double bond is going to be a little bit stronger, and it's going to be a little bit shorter than a single bond. Now, triple bond, 3 rubber bands now around those two atoms, those two spheres. Now it's going to be really hard to pull them apart. So it's going to be a shorter distance that you can pull them, and you're going to have to be much stronger. You're going to have to use more force to pull them apart because that bond is now stronger. So length decreases as the number of bonds increase, and strength increases as the number of bonds increase. So those are the trends that we're going to see between single, double, and triple bonds. So now I'm just going to show 2 quick examples for Lewis dot structures and how we represent these line bonds for covalent bonding. Now I'm not going in order of our steps. I'm not going to count the total valence electrons first. We're actually going to confirm the total valence electrons last. So let's look at H2S first. So dihydrogen sulfide. Now, looking at dihydrogen sulfide, if I was trying to figure out what the central atom was, I see hydrogen is the first atom present in this molecular formula. And I know from the previous slides that hydrogen will not be the central atom. So then I go to sulfur. So sulfur is going to be the central atom. And then these 2 hydrogens, represented by this subscript of 2, are going to be the terminal atoms around that sulfur. So if I were to draw the Lewis dot structure of that, it would look something like this. So notice we have 8 total electrons, represented by these 8 dots. The ones in black, so the 6 dots in black, are from sulfur, because sulfur has 6 valence electrons because it is in group 6 of the periodic table. The green dots are the electrons that hydrogen is contributing to the cause, because hydrogen contributes 1 valence electron because it is in group 1. So usually how we're going to draw this for the bonds themselves, instead of drawing dots like we see here, we're going to represent them as lines. So each line, each single bond, is representing 2 electrons, as you can see from the dots depicted, the green dot and the black dot off to the left. Now the remaining dots we leave as dots because they're not bonded to anything. So this lone pair that is above sulfur, so when we have 2 electrons together we call it a lone pair, and this lone pair that's underneath the sulfur atom, since they're not attached to anything, we leave them as dots instead of putting lines. Let's look at this compound that has phosphorus, chlorine, and bromine. I'm not even going to name that for you because we haven't learned how to name covalent compounds that have more than two elements together. So in this case, central atom, which one is it going to be? It's almost always the first one present in the chemical formula unless that first atom present is hydrogen, and in this case hydrogen is not the first atom present, it's phosphorus, so phosphorus is going to be our central atom. That means these two chlorines and this one bromine are going to be the terminal atoms around phosphorus. So you can start by drawing the Lewis dot structures of each of these atoms. So phosphorus has 5 valence electrons represented by these 5 black dots. And then you'll also notice that chlorine, bromine, and the other chlorine have 7 because they're all halogens. So halogens are going to have 7 or donate 7 valence electrons to the cause. So you'll notice there are going to be 3 bonds forming here. So we have these electrons being shared circled in red here. Also notice that for phosphorus, phosphorus had 3 electrons that weren't paired. So it makes sense that since it has 3 unpaired electrons, that it's going to form 3 bonds to pair up those 3 unpaired electrons. Now, for those paired up electrons, we represent those by lines instead of representing them by dots. All the other electrons that were present in the original structure remain there. We don't draw lines because they are not bonded to anything. Now we said we wanted to make sure that all of the atoms present had a full octet. So I'm going to go ahead and count the octets for each atom present, starting with the terminal atom. So for this first chlorine, it has 2 electrons here. So 2, 4, 6. And this bonded pair here, so this line, since it's sharing it with phosphorus, it can claim both of those. So chlorine claims both of those, and phosphorus can also claim both of those. So chlorine has 8 total valence electrons, so chlorine is happy. Bromine, same thing. It has 3 electron pairs, just like the chlorine did, 1, 2, 3, making a total of 6 electrons. And then that single bond counts as 2 electrons, so bromine also has 8 total valence electrons, making bromine happy. The chlorine off to the right is going to be the same as the chlorine to the left, so we know that has 8 valence electrons as well. Now I'm going to use a different color to confirm that phosphorus has 8 valence electrons. So phosphorus, each single bond counts as 2, so in blue I'll circle those. So we have 2, 4, 6 electrons from the single bonds around phosphorus, and then 8 total because of the lone pair on phosphorus. So phosphorus is also happy and has its complete octet. Now to calculate the total valence electrons, how we would do that is we first write how many atoms of hydrogen are present, and we multiply that by the total valence electrons that hydrogen contributes to the cause, which is 1. We then add that to the number of sulfur atoms and how many valence electrons sulfur contributes to the cause. That gives us a total of 8 valence electrons. And if you look at our picture, we indeed only used a total of 8 valence electrons. Now for PCl2Br, we have 1 phosphorus atom. It contributes 5 valence electrons because it's in group 5. We have 1 bromine atom. It contributes 7. 2 chlorine atoms, each of those contributing 7. So we add all of that together and we get a total of 26 valence electrons. And if you look at our Lewis structure, it does indeed have 26 valence electrons. Let's do some practice problems drawing the Lewis structures for the following compounds. So we're going to go in order of those steps. We're going to start by counting the total valence electrons, figuring out the central atom, all of that good stuff. Now for the first example, strontium chloride, when I find those 2 elements on the periodic table, I see that strontium is a metal, chlorine is a non-metal. So this is an ionic compound. So I know when I draw its Lewis structure, I'm going to have brackets, I'm going to have charges. In order to figure out the valence electrons, I first need to know how many what the chemical formula is. So we need to draw the chemical formula. So we're going back to, I believe it's chapter 2, where we took names and changed them into chemical formulas. So strontium is Sr on the periodic table. It forms a +2 charge when it's in an ionic compound. Chlorine, Cl on the periodic table, it forms a -1 charge when it forms a compound. So the chemical formula, after I do the crisscross method, is going to be SrCl2, indicating that I have 1 strontium atom and 2 chlorine atoms. So to figure out the valence electrons, I take the number of atoms of each and multiply it by the valence electrons that each of those atoms contribute to the cause and add them all together. So looking at that, we have 2 chlorine atoms according to this chemical formula. Each of those chlorine atoms contributes 7 valence electrons because chlorine is in group 7 of the periodic table. So we multiply those two numbers together. We then add that to what strontium gives to the cause. Now we only have 1 strontium atom according to the chemical formula. It's in group 2 since it's an alkaline earth metal, so it will contribute 2 valence electrons to the cause. So once we add the total valence electrons, we get 16 for the total. Now how do we draw the Lewis dot structure for those? Well, for the chlorines, they form a -1 charge. So we put the chlorines in brackets with the negative sign on the outside. Now the reason they have that negative charge is because they gained 1 valence electron each from strontium, because strontium gave away 2 valence electrons total, 1 to each of the chlorine atoms, so that the chlorine atoms could get their full octet. So we draw 8 dots around each of the chlorines indicating that they have their full octet. They have a -1 charge because they have 1 extra electron than they're used to. Now for strontium, we put that in brackets as well with a +2 charge on the outside of the brackets. Notice there are no electrons or no dots around strontium because it gave those dots, those electrons, away to each of the chlorine atoms. So this would be the correct representation of the Lewis structure for strontium chloride. Now let's look at sulfur diiodide. So for sulfur diiodide, the fact that there is a prefix tells me this has to be a covalent compound, but if I wasn't sure, I could find sulfur and iodine on the periodic table, discover they are both nonmetals, and that would tell me that it is a covalent compound. So what is this going to look like? Since there's no prefix in front of sulfur, I know there's only one of them. The di in front of iodide tells me there are 2 iodine atoms. So the chemical formula then is going to be Si2. My first step is to calculate the total number of valence electrons. So to do that, I figure out how many atoms of each element are present and what they contribute to the cause. So for iodine, for instance, iodine has a subscript of 2, indicating there are 2 iodine atoms. Each iodine atom contributes 7 valence electrons because it's in group 7 on the periodic table. Now for the sulfur, there's 1 sulfur atom. Sulfur's in group 6, so it contributes 6 valence electrons. So that means we have 20 total valence electrons to play with when we're drawing this structure. Now I'm going to probably very poorly try to draw it off to the side so you can see the steps before seeing the final result. So for sulfur, the next step once we do the valence electrons is to figure out which one is the central atom. Now the central atom is going to be sulfur because that is the first atom present, and if you look at the electronegativity chart, you'll notice that it is indeed the least electronegative atom present as well. So we have sulfur and 2 iodines, so that means the iodines are going to be the terminal atoms. So I'm going to draw a line indicating a single bond between sulfur and the iodine atoms. Once I do that and I have the regular structure set out, my next step is to make the terminal atoms happy. So how do I make the terminal atoms happy is I want to make sure they have a full octet. So right now, looking at the iodine atoms, each iodine atom currently only has 2 electrons because of that single bond. because remember, this single bond represents 2 electrons and it's sharing those electrons. So each iodine has 2 at the moment. Now, since it only has 2 and it needs 8, we're going to add 6 dots around it so that each of these iodine atoms has their full octet. Has the 3 lone pairs, indicating these 6 electrons, and then the 1 single bond for a total of 8. So once we get to this step, we want to figure out how many electrons have we used, how many do we have left, because any leftovers are going to go on the central atom. So right now we've used 2, 4, 6, 8, 10, 12, 14, 16. I've used a total of 16 electrons, including the single bonds and all the dots that I added. So we had 20 to play with, and we've only used 16. So 20 minus 16 gives us a total of 4 electrons. So that means we have 4 extra left, and the extra go on the central atom. So I'm going to put 2 at the top of sulfur and 2 at the bottom. So now that I've used all of my total electrons, I double check that everybody is happy. I know the iodines are happy. I already counted how many electrons they have around them. Now counting sulfur, each of the single bonds counts as 2, so 2, 4. We have a lone pair on top for 6, a lone pair below for 8. So sulfur also has a full octet and is happy. So the final Lewis structure then is going to look like this. Sometimes in this course, rarely in this course, we'll get Lewis structures that have more than one central atom. That can make things a little more complicated. Now, an example of this is methanol, CH3OH. So usually you can identify if there's more than one central atom because of how they write the chemical formula itself. So notice in this chemical formula, they have hydrogen in 2 different places. Okay, so the reason that they have hydrogen in 2 different places is because they're saying that these 3 hydrogens that are next to the carbon, those 3 hydrogens belong on that carbon. So carbon is the central atom for those 3 hydrogens. Now this other hydrogen that's over here on its lonesome, next to oxygen, the reason it's over next to oxygen is because that hydrogen is attached to oxygen. Okay, so that's usually how we'll tell if there's more than one central atom, is if there are hydrogens or a different atom in more than one spot in the chemical formula. So how are we going to figure this out? We're going to start by counting the total electrons, just how we did in the previous example. So oxygen, since it's in group 6A, it has 6 valence electrons. And there's only 1 oxygen, so that's where we get this 6 from in the formula. Hydrogen contributes 1 valence electron, and there's a total of 4 hydrogens. So 4 times 1, that's the guy here representing the hydrogen atoms. Last but not least, we have carbon with 4 valence electrons, and there's only 1 carbon atom. So we get a total of 14 valence electrons to play with. Now, carbon and oxygen are both going to be in the center. So we'll put carbon and oxygen together with a line in between them. Why are we doing a line? Because it's a compound. It's a molecular compound. They share electrons, so we need to put a bond connecting them. So that line is representing a single bond worth 2 of those 14 electrons we have to play with. So once we get that, we then add the rest. So we know there's only 1 hydrogen attached to the oxygen, and the other 3 hydrogens are attached to the carbon. So we represent that by drawing lines with the hydrogens now. So next step is to make sure the terminal atoms are happy. Well, in this case, the terminal atoms are hydrogen. And remember, hydrogen can't get an octet. It can't get 8 valence electrons. It can only get 2. So you'll notice we'll only see hydrogen with single bonds because a single bond represents 2 electrons. So this single bond is fulfilling hydrogen's shell because it has 2 electrons in it. So now I know all of the terminal atoms, or the hydrogens at least, are happy. Next is to figure out, now that all the terminal atoms are happy, if we have any extra electrons to add. So how many have we used? Looking at the single bond lines, counting each of those single bonds as 2 electrons, we have 2, 4, 6, 8, 10. So we've used 10 total valence electrons. So since we've used 10 total valence electrons, we originally had 14. So that means, since we've already used 10, we have 4 left. So those 4 have to go on a central atom. Now the next question is, are they going to go on carbon or are they going to go on oxygen? They're going to go on oxygen. How do I know they're going to go on oxygen? Because if you look at carbon, carbon's already happy. Carbon already has a full octet because it has 4 single bonds around it, and each of those single bonds represents 2 electrons. So carbon has 8 electrons around it already. So I added the 4 onto oxygen because oxygen only had 2 single bonds representing 4 electrons, and oxygen wants 8, just like carbon does. So if I add those 4 remaining valence electrons around oxygen, it now has 8, and everybody is happy, and this is the correct molecular structure. Covalent bonding with multiple bonds. So sometimes we're going to have double and triple bonds, as we discussed earlier. How to determine if you are going to need double or triple bonds is going to come at the end of your steps when we're drawing Lewis structures. So you'll notice we have the original steps, such as counting the valence electrons, figuring out what the central atom is, and arranging the terminal atoms around it, making the single bonds first, making the terminal atoms happy by making sure they fulfill the octet rule and have 8 electrons around them. And then we always put any extra electrons on the central atom. In some cases, there isn't extra electrons to put on the central atom, and the central atom still doesn't have an octet. So in that case, when the central atom doesn't have an octet, that's when we add extra bonds. And we do that by taking an electron pair from one of the terminal atoms and sharing it to make a bond. We'll go over some of these examples in class. It's very hard to show that process with the slides. Just be aware that these are the general steps for determining if double or triple bonds are needed. Last thing we're going to touch upon is the octet rule exceptions. So every rule has an exception, right? We already saw, for instance, helium and hydrogen are exceptions to the octet rule because they only have an s orbital, so their max is 2 electrons, because you can't fit more than 2 electrons in an s orbital because it only has one orientation, as we saw in chapter 7. But there are more than just those 2. The first exception is electron deficient, meaning there are some elements that like less than 8 electrons, and we just talked about hydrogen as being one of them. Helium is the other one. Helium only likes 2 because it only has room for 2. But there are others that have room for 8 but don't like 8, and those would be beryllium and boron that we're going to see. Boron most often. An example would be boron trihydride, shown off to the left, or excuse me, to the right. So boron trihydride, boron would be the central atom with the 3 hydrogen terminal atoms around it, each bonded by a single bond. Now, when we draw this structure, and if we counted the total valence electrons for boron trihydride, the total valence electrons we would get would be 6. Now notice, with these 3 single bonds, we used all 6 of those electrons. So there's no extra electrons to put on boron so that it can have an octet. Not only that, there's no electrons on the hydrogen atoms, meaning there's no lone pairs on the hydrogen atoms that we can use to make a double bond. So boron is happy staying just like this, just how it is, with 6 valence electrons. Another exception is going to be radicals. So free radicals will also have less than 8 electrons, but they're in a different category than just regular electron deficient because they have an odd number of electrons. They're 1 electron short. So if they have an odd number of electrons, meaning they are very, very reactive. Like you've heard about free radicals in the air and how this gets rid of free radicals and all the advertisements for getting rid of free radicals. Well, since free radicals are so reactive, they can actually cause harm to skin cells. They can even cause cancer in some cases. An example of this would be nitrogen monoxide. So if you do the electron count for nitrogen monoxide, you can see there are 2, 4, 6, 8, 10, 11 electrons when we add them up. Since the total valence electron count is odd, that means there is going to be 1 unpaired electron, as you can see here on the nitrogen depicted in this Lewis structure. So due to that unpaired electron, this is referred to as a free radical. The last exception is an expanded valence. We often call this an expanded octet. This is where we have more than 8 electrons present. This can only happen for elements in periods 3 or higher, and the reason for this is because once we get to the elements in periods 3 or higher, we are now adding in d shells, so the d block. So that means we have extra orbitals, d orbitals, that we can throw any extra electrons in if we need a cause for more than 8. So an example of this would be phosphorus pentafluoride. So for phosphorus pentafluoride, you can see that phosphorus has 5 fluorines around it, each connected by a single bond. Now, since it has those 5 fluorines around it, and those 5 single bonds are 10 electrons, so it has more than 8, and it's allowed to have more than 8 because phosphorus is in period 3 or lower, so it has access to the d orbitals where it can throw the extra 2 electrons into.